Hello, everybody, and welcome to this week's lesson. This week, we are going to be practicing writing and solving one variable linear equations. So grab your pencil and paper, grab your notes from last week's lesson and any of our other lessons where we've talked about functions. We've had a few lessons on those in recent weeks. You will also find your welcome packet useful. The handout in there on keywords and phrases that show up a lot in word problems will be helpful for this lesson as well. You can have a calculator next to you. It might be useful for some of the problems later on. And as always, you should have your formula sheet out next to you, even though we're not going to be using it too much today. All right, so our learning goals for this week. Like I said, this lesson builds a lot on top of our lesson last week on evaluating functions. So definitely go back and either review that lesson or watch it for the first time if you haven't yet before coming back to this lesson. So our learning goals for this week, by the end of this week, you will be able to solve linear equations in one variable, solve real-world problems involving equations, and write linear equations in one variable to represent context. So basically our goal is to be able to write and solve linear equations that relate to word problems and real-world situations. So let's get started. We're going to start with a warm-up problem. This is a problem that we worked on during last week's lesson, so it might look very familiar to you. I chose this problem because it really hits on almost all of the points that we discussed in last week's lesson. So again, you should have those lesson notes out in front of you from last week. Go ahead and pause the video and give this problem a try. When you're ready, start the video back up and we're going to go through it together. So it says, which statement is true about the two functions shown below? So we've got these two functions. One of them is shown on a graph. This function is called f of x, and I know that because we've got the name right up here, f of x. And then the second function is shown in table form, and this function is called g of x, and I know that because my output here is called g of x. So we've got f of x as a graph and g of x as a table. And when I look through my answer choices, we've got a few different topics that the answer choices are touching on here. So choice A and choice B are both talking about the y-intercepts of our two functions. So choice A says that f of x and g of x have the same y-intercept. Choice B says they have different y-intercepts. Choice C is talking about f of x having a higher rate of change. And what's another name for rate of change that we talked about? It is slope. So that's about the slope of the functions. And then choice D is talking about quadratic functions versus linear functions. So again, that is something that we talked about in last week's lesson. So let's start with the y-intercepts. Let's determine the y-intercepts for f of x and g of x so we can compare them, see if they're the same or if they're different. So you want to remember that y-intercept means where the function crosses or intercepts the y-axis, the vertical axis here. So remember, y is always our vertical axis. It's another name for our output in our function. So we can also think of this column here on the table as being the y column, the output column. So for f of x, when I examine the graph here, this red line, I see that this red line crosses the y-axis here. So this is the point 0, -2. This point is at 0 along the x-axis, and it's at -2 on the y-axis. So the y-intercept of f of x is at -2. It crosses the y-axis at -2. Now let's take a look at the second function, at g of x. So if we don't have a graph, if we are just looking at a table or a list of values, one way that we can quickly identify the y-intercept is by looking for where x is 0. So notice here on the graph, the y-intercept was this red point that had an x value of 0. That's always going to be true for the y-intercept of any function. So we can look for that in a table, and if they were kind enough to give us that point directly in the table, it'll make our job a lot easier. All right, we had to pause recording for a moment there for a little scene change to avoid some background noise, one of the joys of recording at home. All right, so where were we? We were talking about how to identify the y-intercept if we're looking at a table of values. And first thing you should always check for is to see if they've just given it to you in the table. And in this case, for this table of g of x, we do in fact have the y-intercept right there for us. And we know that because we're looking for the point where x is 0. So here is the y-intercept for g of x. This is the y-intercept. And so we can see that they actually do have the same y-intercept. F of x has a y-intercept at 0, -2, and g of x has a y-intercept at 0, -2. It's the same one. So it should be the case that choice A is the correct answer. We know it can't be choice B because they're not different. But let's go ahead and let's take a look at choices C and D just for a little review of these concepts. So choice C is talking about rate of change or slope. Slope is a measure, well, it's a measure of the rate of change, or another way to think of it is the steepness of a line. So how fast is the line increasing or decreasing? So let's try and see if we can determine the slope for f of x and g of x. Now, slope really only applies to linear functions. So what is a linear function? It's a function with a constant slope is one way to define it. Another way to define it is when you look at the graph, it's a straight line. So when we look at f of x, we can see that red line there. It's a straight line, so we know f of x is a linear function. We can figure out the slope of it. One way to figure out slope on a graph is just by visual inspection. So slope is the ratio or the comparison of change in y. Remember, we use that little triangle symbol as shorthand for change. So change in y compared to change in x. That's how we determine slope. So I'm just going to pick 2 points on the line, any 2 points where the points are at nice whole numbers. So you don't want to be picking a point that's like in between whole numbers. You'll have to guess at the decimal amount. We don't want to do that. We want to pick points at nice whole numbers. So I'm going to go ahead and I've already got 1 point on here, this red point. I'm going to pick a second point located right here. So this yellow point. Now this yellow point is at, so it's at 3 on the x-axis, and it is at 0 on the y-axis. Okay, and so to determine slope, we need to figure out going from one point to the next, how much do we need to go up? So what's our change in y? And how much do we need to go over? What is our horizontal or our change in x? So to get from the red point to the yellow point, I need to go up 1 space, 2 spaces. So my change in y is 2, positive 2, because we're going up. And then I need to go over 1 space, 2 space, 3 spaces. So over an increase of 3. So my slope for f of x is 2 to 3, or 2/3. Two-thirds. And remember, the higher the slope, so the larger the number is for the slope, the steeper the line. So this slope is a fraction. It's an amount between 0 and 1. So it's not a very steep line. It's not going up super fast. Now let's take a look at g of x. So when we're trying to determine slope for slope of the table, what we want to do is we want to observe, again, the change in y, so the change in the output column, compared to the change in x, the change that we see in the x column. If it is, in fact, a linear function, we should see a consistent change. So let's see here. In the x column, we go from 0 to 1. So that's an increase of 1. In the y column, or the g of x column, we go from -2 to +2. That's an increase of 4. But if you have -$2 in your bank account, and then the next day you have $2 in your bank account, that means your bank account has increased by a total of $4. So the slope we observe there, so change in y, change in output compared to change in x, change in input. I've lost my cursor. There it is 4 compared to 1. Now, if this is a linear function, we should see that same ratio throughout all of our points here. So same ratio, equivalent ratios. So it could be 8 to 2, it could be 12 to 3, but as long as it's an equivalent ratio or an equivalent fraction. I think in this case, we're going to find that it is exactly the same throughout. So going from 1 to 2 is an increase of 1. Going from 2 to 6 is an increase of 4. So we see that the slope is remaining constant, or the rate of change is constant. 2 to 3 is an increase of 1. 6 to 10 is an increase of 4. Staying the same. 3 to 4 is an increase of 1. 10 to 14 is an increase of 4. So we're seeing a constant rate of change. We're seeing a constant slope throughout g of x. And so that tells us g of x is in fact linear. And so it does make sense to calculate a slope for g of x. And the slope is 4 to 1, or 4 over 1, which we can simplify to 4. So g of x has a slope of 4, f of x has a slope of 2/3. Which one of those numbers is larger? The whole number is larger. 4 is larger. So choice C, which says f of x has a higher rate of change, that is not true. It's g of x that has the higher rate of change, or the higher slope. And finally, on to choice D. So choice D says g of x is a quadratic function, whereas f of x is linear. And while we were just talking about slope, we determined that g of x was in fact linear because it has this constant rate of change. It has this constant slope of 4. So choice D also is not true. G of x is not a quadratic function. Both of these functions are linear. They make straight lines. All right. So now on to linear equations. We have already seen 2 variable linear equations in our work on functions. So what we were just talking about in our warm-up problem, right? A 2 variable linear equation is a relationship between 2 variables, 2 quantities, where the rate of change is constant. So that slope that we were just talking about. And you want to remember our definition for equation, which we talked about before. An equation is when 2 things are equal to each other. More specifically, it's a mathematical statement that 2 expressions are equal. An expression is just a sequence of numbers, variables, and operations. So an expression can be something very similar, like very simple, sorry, very simple, like 4, just the number 4, or it can be a combination of a bunch of stuff. So we could say 4 times a variable x minus 2, and all of that divided by 2. So expressions can be very simple, or we can build them up to get a little more complicated. But basically, an expression is just some kind of math stuff, and then an equation is saying that 2 things of stuff are equal to each other. Okay, so let's start here with a little reminder of 2 variable linear equations and how they relate to real life situations. We've looked at some examples like this in the past. So we're going to look at this before we move to 1 variable linear equations, which are actually a little bit simpler. So that'll be nice. So Marta is a salesperson who works on commission. Each week she earns a base salary of $200 plus 25% of the sales she makes. Write an equation that represents Marta's weekly pay. So we're trying to represent her total weekly pay. Let Y represent her weekly pay, and let X represent the dollar amount of sales that she makes. Okay, right, because the amount that she makes is dependent on how much sales she makes for her company, right? She gets a cut of the sales or a commission of the sales. So it says Y represents her weekly pay. And we want to write an equation that represents this. So we want to write an equation or basically a summary of what goes into that weekly pay. What calculations is she doing when she's calculating up her total weekly pay? Well, she earns a base salary of $200. So each week she's always going to get those $200. And then in addition, so plus, she makes plus 25% of the sales she makes. So that keyword there is very important. It's showing us that these are all components of her paycheck that are getting combined or added together. So $200 base salary plus her commission. Now, how do we express this using the language of algebra? How do we express 25% of the sales she makes? Well, we know the sales she makes, that's going to be X. So instead of writing the sales she makes for her company, we just need to write the letter X. And we want 25% of that amount. Now, whenever you're talking about finding a percent of or a fraction of something, that's going to be multiplication. So like half of 10 or 50% of 10. What you mean when you say that is you mean 50% times 10 or half times 10. So we're going to take that keyword of and let that guide us in knowing we need multiplication here. So it's going to be some number times the sales she makes. And now we could just write 25% here, but that's not usually how we would write it. Usually we would take that 25% and change it to either a decimal or a fraction, right? 25% means the same thing as a quarter of something. But most often you would probably see it written as a decimal, especially if we're talking about an equation that we're using to calculate payment. We're probably going to be using decimal numbers. So what is 25% written as a decimal? 25% as a decimal is 0.25. 25% means 0.25 of something. So in summary, Marta's weekly pay is going to be equal to her base salary plus 25% times the total sales that she makes for her company. So this is a 2-variable linear equation that shows the relationship between the amount of sales, the amount she makes in sales, and her total pay for the week. Now, another way you could have written this equation is you could have written it with those two addition terms flipped around. So you could have written this as 0.25x plus 200, oops, don't forget the x, plus 200. That's another way you could write this. Right, with addition, the order that you write things in doesn't matter, so we can flip those things around. And with an equal sign, right, we're saying the two different sides of the equal sign are the same. So you could, if you wanted to, flip the two sides of the equation without changing the meaning at all. So you could say, well, what goes into Marta's paycheck? Well, it's the $200 plus the cut of the sales that she gets. And that results in her total pay. So we can flip the two sides of the equation. So there's a few different ways that we can write this equation that all mean the same thing. And remember that this equation is really just mathematical shorthand that summarizes the information in this paragraph. It's just two different ways of talking about the same thing. One of them is in English, and another one is in the language of algebra. All right, so let's move on to a one variable linear equation. So we're going to start with a similar setup here. Marta is a salesperson who works on commission. Each week she earns a base salary of $200 plus 25% of the sales she makes. This week, Marta earned $800. Write an equation that represents Marta's weekly pay based on her sales X. So really the only difference between this problem and the last example is that instead of just saying Marta's weekly pay, so whatever it happens to be, Y, right, the letter Y, now we are actually told specifically that this week she earned $800. So instead of just talking about a general situation, right, whatever her weekly pay is, we're talking about a specific week where she makes $800. So how did she get that $800? What went into that paycheck? Well, she had her base salary. She had her base salary, and then she had the cut of the sales, right? So she had 0.25 of whatever sales she made for her company. So note, this problem is not asking you to figure out how much she made in sales. That's not what's going on here. This problem is still just asking you to write an equation that represents the situation. So we don't care what X is. We now have enough information that we could figure it out, but we're not there yet. We don't need to worry about that. We're just trying to write a mathematical summary of the situation. So that $800 paycheck is made up of the $200 base salary plus the 25% of her sales. And that's all there is to it. Okay, so let's get some more practice here. Go ahead and pause the video and give these two problems a try. And when you're ready, jump back onto the video and we're going to go through them together. Okay, so number one, Hannah is renting a moving truck. There is a rental fee of $20 plus 25 cents per mile. If she pays a total of 30, choose the equation below that represents the number of miles she drove, X. So again, this is kind of a similar setup where we've got this total amount, this $30, and we're thinking about what goes into that total amount. We look at all of the answer choices here. Each of them kind of follows a similar pattern where the total is on one side of the equal sign, and then it's up to us to choose the correct components that go on the other side. So let's think about what goes into that total bill that she's getting, or that total amount that she has to pay. So she definitely has to pay the rental fee, right? So we know that that $20 has to be there. And then she's also going to have to pay 25 cents per mile. So if she has some number of miles that she's driving, how would you calculate the amount she has to pay for those miles? So let's say she drove like 2 miles. Well, it's going to be 25 cents for the first mile and then 25 cents for the second mile. It's going to be 2 times 25 cents, right? So the way that we're calculating that mileage fee is we're taking the rate per mile, so the 25 cents per mile, and multiplying it by the number of miles that she drove. In this case, we don't happen to know yet how many miles she drove. We're not asked to figure that out. We just want to sort of write out what goes into that total amount of $30. So she definitely has to pay the $20 rental fee, and she has to pay 25 cents times the number of miles that she drove. So when I look down my answer choices here, choice A doesn't even include the number of miles. It doesn't include our variable X, so it definitely can't be choice A. Another way we know that is choice A isn't actually a true equation. It's saying that 30 is equal to 25 cents plus 20. 25 cents plus 20 is not equal to 30. It's equal to 20, 25, right? So choice A doesn't even work as an equation. Now, if we look at choice B is saying, well, her $30 is going to be equal to 25 cents times the number of miles she drove, and then plus that rental fee that she has to pay. So choice B is the correct answer. Choice B has those two components, the $20 rental fee and the 25 cents times the number of miles. Let's take a look at choice C and D just to see why they don't quite work. So choice C is similar to choice B, except it's got these parentheses in it. So what these parentheses are saying, there's a couple different ways you could think about it, but one way to think about it is the parentheses are saying, take the number of miles and add it to the rental fee, and then multiply that total, multiply that sum by 25 cents. Now, I don't know about you, but I'm not really sure how I would take miles and add it to dollars, right? Miles and dollars are two different things. We can't really combine them together into one thing, right? Like if I'm 5 feet tall and you weigh 200 pounds, what's the sum of our height and weight? Well, I guess we could take those two numbers and add them together, but it doesn't really mean anything, that total amount. It's a combination. It's just sort of like we smash them together into this big mess. So we want to be wary, we want to be careful about choice C, because it's asking us to add together two essentially different types of things, which is just not meaningful. It'll give us a bunch of nonsense, which we don't want in our equation. Another way to think about it is that the 25 cents is going to be multiplying the number of miles, but it's also going to be multiplying the rental fee. Now, that rental fee is just a rental fee of $20. It doesn't depend at all. It's not affected by the mileage rate, right? That 25 cents is connected to the number of miles. It is not connected to that rental fee. She's got to pay that rental fee no matter what. So that's another way we might look at choice C and know that it doesn't quite work. All right, and then let's look at choice D. So again, choice D is quite similar to choice B. However, instead of addition, we've got subtraction. Now, those of you who are a little bit familiar with solving equations, with finding a solution, figuring out the number of miles she actually drove, some of you may have been tempted by choice D, because you might be thinking, well, in order to figure out the number of miles, I have to take the total and then I subtract the rental fee. And that's going to get me on the path to figuring out the number of miles. But those of you who are thinking about choice D, that means you're jumping the gun a little bit, because we're not trying to figure out what x is yet. We're just trying to write out an equation that accurately describes the situation. So if we think about what this equation is actually saying, this equation is saying in order to get this total amount of 30, we would take 25 cents times the number of miles and then subtract the rental fee. But that doesn't really make sense, right? Because your total bill, you don't get to subtract the rental fee in order to calculate your total bill. You have to take your mileage fee and take your rental fee, and you got to combine them together to get the total amount. So choice D is not going to work either. So choice B is our final answer. And again, it kind of follows that similar pattern that we saw in that previous example, where on one side of the equal sign, we've got a total amount. And on the other side of the equal sign, we are combining the components that go into that total amount. All right, let's look at number 2 here. So Jerome earns $19 an hour as a medical resident. So he just finished med school. Exciting for Jerome. This week he earned $1,330. Choose the equation below that represents the number of hours he worked, and we're going to call that X. Remember, we're just using the letter X here because it's kind of a habit among people who are doing math. You could actually choose whatever letter you want. The letter is just a placeholder for a changing or an unknown number. So the letter is not super important. All right, so if we look at our 4 answer choices here, we see that on one side of the equal sign is the total amount, his total earnings. Even though it's flipped around from the last example, right? The last example had the total amount on the left side of the equation. In this example, we have the total amount on the right side of the equation. Doesn't matter, right? It's an equal sign, so you can flip things around. They're still equal. So let's go through these answer choices. Remember, we want to, since the total earnings are on one side, we want to be thinking about what goes into the total earnings. How do you calculate the total earnings based on that hourly amount? So let's look at choice A. Choice A, right away, we know that's not going to work because it doesn't even include his hours that he worked. It doesn't include the variable. Also, we know it's not going to work because it's a false statement. It's saying 19 is equal to 1,330. That's just not true, right? That's definitely not a true statement. So we don't want to pick this nonsensical statement as our choice here. Let's take a look at B. So B is saying $19 an hour times the number of hours is equal to his total earnings. That sounds true to me, right? If you want to calculate your total earnings for a week, you would take your hourly wage times the number of hours you worked, and that's going to give you your total amount. So choice B is going to be our correct answer here. Let's take a look at choice C and D just to talk about them. So choice C is saying $19 an hour plus the number of hours he worked. Now, this is definitely not going to give us the correct number unless he worked 1,311 hours in 1 week. Adding these two numbers together is not going to give us a total of 1,330. So when you're calculating your total earnings, you're taking your hourly rate times the number of hours. You're not just taking your hourly rate plus the number of hours you worked. So choice C isn't going to work. Another way you can think about it is choice C is asking us to add together 2 different types of things, right? The 19 is a dollar amount. It's $19 per hour. And X is just hours. So what does it mean to add dollars and hours? We can't really we can't really smush them together into the same group because they're two different types of things. All right, and then choice D is saying take the number of hours that he worked, divide it by $19 an hour, and that's going to give you his total earnings. Now, this is kind of the same issue from choice D in the last example. Those of you who have some experience with solving equations may have been tempted by the division, because you might have been thinking, well, in order to figure out the number of hours that he worked, we'd have to take the total amount and divide it by his hourly rate. And you would be correct in thinking that. However, this problem is not asking you to figure out how many hours he worked. It's asking you to choose an equation that accurately represents the situation. So it's true that, all right, are we recording still? Yes. Having some internet issues today, folks. All right, let's get back to our lesson here. So, where was I? Right, I was saying that the division in choice D, so division could be used to figure out the number of hours that he worked, but that's not what you're being asked to do. In this situation, you are being asked to choose an equation that accurately represents the situation. And taking the number of hours he worked dividing by $19 is not going to give you his total earnings. So choice D also isn't quite right. Okay, so we just had some practice with writing equations to represent situations, or choosing equations that represent situations. Now we are going to practice solving those equations. So actually figuring out how many miles did Hannah drive, or how many hours did Jerome work. So when we have an equation with just one variable. So if you only see one variable in the equation, not two different letters, two different variables, most of the time that means you are going to be able to solve for that variable. You're going to be able to figure out what that missing number is. Sometimes it'll be quick and easy, just one or two steps. Sometimes it can be a little bit more complicated. What we're going to focus on today is we're going to be focusing on solving basic one variable linear equations. So those are equations that involve just one or two steps to solve them. So when we say solving an equation or finding a solution is a value for a variable that makes the equation true. So both sides are actually equal. Last week we practiced evaluating functions. So I have an example here of a linear function, and then if we're told a value for x, we can figure out the corresponding value for y, right? So if we're given an input value, we can figure out the output. What we're doing here is kind of similar in that we're trying to determine a value, but it's not quite the same thing, because what we are going to be doing is we are going to be trying to determine the value of x. So trying to determine the value of a variable that's kind of buried inside of these other numbers and operations. We're going to have to do some detective work. We're going to have to work backwards a little bit to figure out what that value is. So the basis of solving a one variable linear equation is using inverse operations. That's what you're mainly going to be thinking about and using when you are solving these equations, when you're trying to find these missing numbers. So, right, operations are the things that we do with numbers: addition, subtraction, multiplication, division, exponents, and roots. Inverse operations are the pairs of operations that cancel each other out or undo each other. Another way to think of it is opposites. So adding and subtracting are opposites of each other. They undo each other, they cancel each other out. Multiplication and division also are opposites or inverses, they cancel each other out. And then exponents and roots are opposites. Now today in these linear equations, we don't need to worry about exponents and roots, so you can set that aside. Okay, so we're gonna start with one-step equations. These are really the most basic types of equations that we might be asked to solve, so that's why we start here. And they're called one-step equations because they only involve one operation that we need to cancel out or undo. So I've got 4 examples here for the 4 different operations that we might encounter. The first example, we see that on the side with the variable, we've got addition. In the second example, on the side with the variable, we've got subtraction. The third example, on the side with the variable, we've got multiplication. And the fourth example, on the side with the variable, we've got division. So we're gonna see how to tackle one-step equations with these 4 different operations. Now, when you are solving an equation, your ultimate goal, so always your ultimate goal when you're solving an equation, is to isolate the variable or to get the variable by itself on one side of the equal sign. So your goal is to isolate the variable. That means you're trying to cancel out or get rid of all of the other stuff besides the variable, all of the other stuff except the variable on whichever side the variable happens to be sitting. So that means when you first look at an equation, especially linear equations like this, one-step linear equations, at first you don't even really need to worry about the number that's on the other side of the equal sign. You should be laser focused on the side that contains the variable, whichever side that is. So let's start with the first example here, the addition example. When I look at the equation, I'm going to focus on the left side because that's the side that contains the variable. And I see on that side, the variable is being added together with 2. So in order to get the variable by itself on the equal sign, remember that's my ultimate goal, is to have something that looks like this, where x equals some number. In order to do that, that means I need to get rid of this 2, right? I need to cancel it out. So if you are adding the 2, the way that you get rid of that or cancel it out is by doing the inverse, by subtracting. So to cancel out that 2, I'm going to, from the left side of the equation, I'm going to take away 2. And then, so adding 2 and then taking away 2, those 2 actions cancel each other out. You end up with nothing. You end up with 0. So 2 minus 2, that goes to 0. And then since this is an equation, it's a statement that the 2 sides are exactly the same. They're exactly equal to each other. If I make a change to one side of the equation, whatever change that is, I need to come over to the other side of the equation and do exactly the same thing. So I'm going to come over to the right side of the equation and do the same thing. I'm going to subtract 2. Okay. So now I come down here, I'm gonna bring down my equal sign. The equal sign should always be sort of sitting in the middle of whatever you're doing. On the left side of my equal sign, I wanna think about what do I have remaining? So I've canceled out my 2. I canceled out that addition. What do I have left? I just have x, right? So I have x remaining here on the left side. And then over on the right side, right, I had 10 minus 2. What is that equal to? It is equal to 8. So we have x equals 8. Now, when we were looking at this original equation, right, it was saying 2 plus some number equals 10. It's very likely that you could have just looked at that equation and figured out what that missing number had to be, right? I know I am confident that all of you know that 2 plus 8 equals 10, as long as you've had your morning coffee. So 2 plus 8 equals 10. Of course, that's true. So with a lot of these one-step equations, you might be able to look at them and figure out what the missing number is without going through all of this stuff with inverse operations. However, what we are doing right now is we are building up our toolkit so that when we get to more complicated equations, we know what tools we need to use to figure out the solution. So with a very basic equation like this, you might be able to just look at it and figure out the answer. But when you get to more complicated equations, that's not going to be the case. You're not going to be able to just know it off the top of your head. And trying to kind of guess and check and figure it out is going to be a more involved process. It's going to be more time consuming and more difficult than just going through these steps that we're practicing. So I challenge you to, even if you can look at these equations and figure out the missing number in your head, I challenge you to go through these steps that we're practicing anyway. The fact that you can figure out the missing value in your head is still useful because you can use that as a guide to see if you are coming up with the correct solution, right? So if you look at 2 plus x equals 10 and you know, okay, x has to be 8. Well, when you go through your steps of canceling out everything but the variable, right? When you go through the steps of isolating the variable, you better get x equals 8. And if you didn't, you know that something went wrong because you know the answer has to be x equals 8. All right, let's take a look at the second example here where we are using subtraction. Gotta find my cursor again. Where did it go? Likes to disappear. Okay, there it is. We have x minus 5 equals negative 1. So I see we've got our variable and then what's happening to the variable where, well, we're taking away 5 from it. So we want to cancel out that action of taking away 5. We want to cancel out that action of subtracting. And how do we do that? We do that with the inverse. So since it says minus 5, what I'm going to do is I'm going to add 5, minus 5 plus 5. Those will go to 0, they'll disappear. Since I added 5 on the left side of the equation, I need to come over to the right side and do the same thing, add 5. So I'm going to bring down my equal sign. Think about what we have on the left side of the equation. Well, we canceled out our minus 5, so all that's remaining is x. On the right side of the equation, we had negative 1 plus 5, which equals 4. And that's our final answer. Our variable, we successfully isolated the variable on one side of the equal sign. So x must be equal to 4. And if we return to our original equation, that makes sense, right? We would be saying 4 minus 5 equals negative 1. All right, let's take a look at example 3, our multiplication example. It says 4 times some number x equals 36. So what's happening with the variable on the left side here? Well, it's being multiplied by 4. How do we cancel out multiplication? We cancel it out with its inverse. We cancel it out with division. So I'm going to divide this side by 4. Multiplying by 4 and then dividing by 4, those actions will cancel each other out. Basically, 4 divided by 4 is 1. And 1 times x is just x, right? So it all goes away except for the x. Since I divided by 4 on the left side, I need to come over to the right side, do exactly the same thing. And what am I left with? Bring down the equal sign. On the left side, I've got just my variable x. On the right side, 36 divided by 4 is 9. And that checks out with our original equation, right? 4 times 9, right? 4 times x, 4 times 9, is in fact equal to 36. So that makes sense. All right, on to our final example here, number 4, involving division. So notice that the variable is on the other side of the equal sign. Doesn't matter, has no effect at all on how we solve this equation, we still have the same goal to isolate the variable on one side of the equal sign. Doesn't matter if it's the right side or the left side. So this is saying 30 is equal to some number divided by 3. So some number divided by 3 is equal to 30. All right, so let's just focus on the side with the variable here. It says x divided by 3. Well, what is the inverse of division? The inverse is multiplication. So I'm going to multiply this side of the equation by 3. And as we saw in the previous example with multiplication, right, we know that multiplying and dividing, they cancel each other out. So these 3's will cancel each other out. Since I multiplied by 3 on the right side, I need to come over to the left side and do exactly the same thing. And now I'm going to bring down my equal sign and write out what I've got now. So on the right side of the equation, all that's remaining is the x. And on the left side of the equation, we had 3 times 30, which equals 90. So we have 90 equals x, or x equals 90. Which again, if we return to our original equation, right, 30 equals some number divided by 3. We now know that what we were saying was 30 equals 90 divided by 3, which is true. That makes sense. Okay, so when we're solving one-step equations, our goal is to get the variable by itself on one side of the equal sign. And we do that using inverse operations. So adding, subtracting, multiplying, dividing. All right, now on to two-step equations. So in the last examples, we had equations that only had one operation in them. Now we're gonna look at what we do if we've got two operations to deal with. And the way that we deal with it is we follow a certain order. So with two-step equations, you, in general, are going to cancel out addition and subtraction first, and then you'll cancel out any multiplication and division second. Where does that order come from? Well, it actually comes from the order of operations, which might sound a little weird because the order of operations tells us that multiplication and division come first. Lost my cursor again, guys. Hold on. It'll reappear any minute. There we go. So the order of operations, right? We've got parentheses, we've got exponents. We're not really worried about those things right now. And then we've got multiplication and division. And we've got addition and subtraction. So the order of operations tells us what order we do things in when we are doing calculations. But when we're solving equations for a variable, we're not really doing a calculation. We're kind of undoing a calculation. We're trying to cancel out calculations. So instead of following the order of operations, what we do is we start at the end and we work backwards. So we tackle addition and subtraction first, we cancel those out, and then we cancel out multiplication and division. All right, so let's take a look at the first example here. So in this first example, just focus on the side with the variable. We've got multiplication and we've got addition, right? So if we think about what's happening to the variable, well, the variable is being multiplied by 2 and we're adding 10. So what we're gonna do, we're gonna tackle that addition first, and then we're gonna tackle the multiplication. I'm gonna cancel out the plus 10 by doing minus 10. Those will go to 0. I'm gonna come over to the other side, do exactly the same thing. And then I'm gonna bring down my equal sign and write out what I have remaining on each side. So on the left side, what I have remaining is 2x. And on the right side, what I have remaining is 30. Okay, So the addition's gone, and now all I have to worry about is this multiplication. How do we cancel out multiplication? We do it with division. 2 divided by 2 is 1. 1 times x is just x. So effectively the 2's cancel out. Come over to the other side and do exactly the same thing. Divide by 2. Bring down the equal sign and think about what we have remaining on each side. So on the left side, we have x. And on the right side, 30 divided by 2 is 15. And we solved it. So if 2 times x plus 10 equals 40, then it must be that x equals 15. X must be 15. And right, you can always double check your answer by going back to your original equation and plugging it in. So you would say 2 times 15 plus 10, and double check to see if that really does equal 40. 2 times 15 is 30, and 30 plus 10 is, in fact, 40. So we did a good job. All right, next example here. I see division, right? X over 6, x divided by 6, and I see subtraction. We're going to cancel out the subtraction first. Come over to the other side, do the same thing. Bring down the equal sign. What do we have left? We've got x over 6 on the left side, and we've got 4 on the right side. So the subtraction's gone. Now I need to cancel out this division. How do I cancel out division? I cancel it out by multiplying. So multiply the left side by 6. Multiplication and division will cancel. Multiply the right side by 6. Bring down the equal sign. And what do we have remaining? We've got x over here, and we've got 24 over here. And that's our final answer, x equals 24. If you return to the original equation, what we're saying is that 24 divided by 6 and then subtract 2 is equal to 2, which is actually true. So we did a good job again. All right, let's tackle this third example here. So it says 7 minus 2x equals 3. Now, this third example is slightly different. So it's subtraction and multiplication, both of which we've seen before. However, with subtraction, order is important. And so far, we've only seen examples where the variable term or the variable comes first, and then just a regular number comes second. So it'd be like the variable take away 2, or the variable take away 5, whatever it is. But here, we are taking away the variable, right? It's 7, and then take away 2 times x. So we're going to have to think about this ever so slightly differently. There's a couple different ways to tackle a problem like this. I'm going to show you the way I like to do it. If you are interested in seeing another way to do it, you can get in touch with me and we can go through that one-on-one. So when I look at this, I see I've got this 7 that needs to get canceled out, and I've got this minus 2 that needs to get canceled out. If you have a 7, how do you cancel out a 7? Just a regular 7. It's not a 7x, just a 7. How do you cancel out that 7? How do you make it disappear or go to 0? Well, you make it go to 0 by taking away 7. Right? 7 minus 7 is in fact 0. So those 7s will go away. And then over here, we do the same thing. Take away 7, not 4. I just started writing 4 for some reason. Okay, bring your equal sign down and then think about what you have remaining. So on the left-hand side here, we canceled out the 7, and that means what we have remaining is the minus 2x, or the negative 2x. And then on the other side, we had 3 minus 7, which is negative 4. Okay, So let's talk a little bit more about that subtraction we just did. Another way to think about it, another guiding principle that you could have for yourself is to focus on the sign in front of the number and use that to help you cancel out the number. So for example, in the first example here, if we were to just block out this 2x, if we were to ignore it, we would say we would see that we just have a plus 10 or a positive 10. And how do you get rid of a positive 10? How do you make it disappear? Well, you need to take away 10. You need to minus 10. In the second example, we have x over 6 minus 2. If we block out this x over 6, we just focus on the minus 2. Well, how do you get rid of negative 2? How do you make it go to 0? You need to add 2 to it. So we did plus 2. And in our third example here, if we just focus on that 7, we block out everything but the 7. We just focus on what's in front of it. So there's nothing in front of it. When there's nothing in front of a number, we assume it's positive, right? You could write plus 7 here and it would mean the same thing. So since it's a positive 7, we needed to do the opposite. We needed to do minus 7 or take away 7. So that's another way to think about it, is to use the sign in front of the number as your guide for helping you cancel out the number. All right, so now we've taken care of all that addition and subtraction nonsense, and now we just have multiplication left. So how do we cancel out multiplication? Right, because we're not trying to cancel out the minus 2x, we're just trying to get rid of that minus 2. We want to leave the x alone. We don't want to touch the x. So to cancel out multiplication with minus 2, we need to divide by minus 2. Those will cancel. Do the same thing to the other side. Bring down your equal sign. What do we have remaining on the left side? On the left side, we just have x. We've isolated our variable. And on the right side, we had negative 4 divided by negative 2. With multiplication and division, when you have two numbers of the same sign, so both positive or both negative, you get a positive answer. So negative 4 divided by negative 2 is 2. So if we return to our original equation to check our answer, we would be saying that 7 minus 2 times 2 equals 3. So that's really saying 7 minus 4 equals 3. And that's true, right? 7 take away 4 equals 3. So we solved our equation correctly. The solution is 2. All right, so we got a couple practice problems here. These are our last 2 practice problems, and then we're going to wrap it up for today. So again, pause the video, give these a try, and then we're going to go through them together. Number 1, Tori is planning to sell some t-shirts in her store. The following equation shows how much she'll have to pay for the shirts based on the number of shirts she orders from the supplier. If so, C equals $5.99 plus $1.50 times T. If Tori can pay $80.99 for the shirts, how many shirts can she order? So let's think about this equation. It says the equation shows how much she'll have to pay. So the total cost, right? Capital C, how much she'll have to pay, the cost, based on the number of shirts, the number of t-shirts she orders. So the cost is equal to $5.99 plus $1.50 times the number of shirts that she orders. That's T there. So if she can pay $80.99 for the t-shirts, how many shirts can she order? So that $80.99 is her maximum cost, right? She can't have a cost of more than $80.99. So what we're trying to figure out is if her cost is $80.99, how many shirts did she order? What was the maximum amount of shirts that she ordered? So assuming that her cost came out to that $80.99, what does that mean for the number of t-shirts? Okay, so we've got this equation here. We've got a one variable equation. We're going to solve it for the number of shirts that she ordered. So now we're just going through those steps we practiced. I see on the side with the variable, I see addition and I see multiplication. That means I'm going to cancel out the addition first. What's being added to the variable? Well, it's $5.99 that's being added. So I need to cancel out the $5.99. Let's pick another color here. Cancel it out by taking it away. Minus $5.99. Minus $5.99 from the right side of the equation, and also minus $5.99 from the left side, right? Same thing to both sides. Bring down the equal sign. What do we have remaining? Well, we've got 150 times t over here. And then we've got $80.99 minus $5.99 over here, which gives us 75. So what's next? Well, we want to cancel out that multiplication with division. We're going to divide by 150. Cancel those out. Same thing to the other side. Now you could do this with long division. However, if this was an actual test problem, it is almost 100% certain that this would show up on the calculator section of the test. And so you'd be able to use your calculator to do 75 divided by 1.5. Not because you can't do it by hand, but just because it's a little bit quicker on the calculator. So 75 divided by $1.50 is 50. So I got 50 remaining on the left side, and I've got just T over here. So the number of t-shirts that she ordered was 50, right? 50 t-shirts got her to that total cost of $80.99. All right, our final problem for today, number 2. 30 is equal to the sum of 6 and twice an unknown number. What is the unknown number? All right, so this problem is kind of interesting because it's not really giving us a real world situation. This is more like a riddle or a puzzle where we need to figure out the unknown number. Now, it's possible that you could just do a little guess and check here. You could try and do it that way. But another way to do it is to use the information given to us to set up an equation and then solve that equation. So let's see what that looks like. We're going to look for some key words here. It says 30 is equal to. Right away, I'm going to start translating this into an equation. 30 is equal to. And then I see the sum of. What does sum mean? If you're looking at your keywords handout, you'll see that sum means addition. So sum is what you get when you add two things together. So we have the sum of 6 and something else, right? The sum of 6 and twice an unknown number. So 6 and twice an unknown number. Now that unknown number, that's our variable. That's the missing piece of this puzzle. You could call that N, you could call it J, you could call it K, you could call it smiley face, you could call it question mark. I'm gonna call it N for number. So twice an unknown number. Twice means 2 times something, right? Twice of something means you did it 2 times. So we're gonna do 6 plus 2 times our unknown number. So 30 is equal to the sum of 6 and twice our number. What is the unknown number? Well, now we've got ourselves a nice 2-step linear equation that we know how to solve. So I focus on the side with the variable. I see addition, I see multiplication. We're going to tackle that addition first. Same thing to both sides. Bring down the equal sign. We got 2n remaining over here. We got 24 remaining over here. Now we need to cancel out the multiplication with division. Cancel those out. Same thing to both sides. Bring down the equal sign. We've got our variable remaining over here, and we've got 12 remaining over here. So our missing number was 12. 30 is equal to the sum of 6 and twice 12. The sum of 6 and 2 times 12, or the sum of 6 and 24. All right, guys. Well, if you made it this far, congratulations. This is your to-do list for the week. So you have just attended one Zoom lesson or watched the recorded lesson. I definitely encourage you to go back and look over things that were a little tricky for you, gave you trouble. Repetition is a huge help in getting things to stick in your brain. So never be afraid to watch things more than once. This is a summary of the posts and assignments you're going to see show up on our Google Classroom throughout the week. So if you're watching this, that means all of the stuff from Monday has already gone up, as well as the stuff from Tuesday. So your problem of the day from Monday, the intro post, your vocab list, and online learning links. If you had any difficulty with the stuff that we went over today, I would highly recommend the vocab list and online learning links post. It's going to have links to additional shorter videos that just give a little more explanation and examples of what we went over today, given by different teachers. So sometimes it can be helpful to just have a different voice in your ear, have a different person's perspective on the topics we are covering. So problem of the day assignment is up. Your vocab quiz assignment is up. Tomorrow on Wednesday, or whenever you're watching this, on Wednesday, your Worksheet Wednesday assignment is up. You should plan to devote about an hour to that assignment. On Thursday, there's going to be a study skills post. That's optional, but remember we've talked about how studying and learning is a skill, just like anything else, something that you need to practice, something that you need to figure out what works for you. So in those study skills posts, I'm just going over different strategies, different tips that can help you be a better learner. And then on Friday, you've got your final problem of the day assignment. So that is 3 main assignments that you're working on, bonus assignment if you complete the vocabulary quiz. Get in touch with me if you have any questions about any of this stuff, and I hope you're having a great week. Take care.